Hello everyone. We are celebrating the World Food Safety Day 2025 on 7 June. The theme of the day this year is Science in Action. Food safety is a non-negotiable aspect of any food, and scientific approach is the cornerstone of ensuring food safety. On this occasion, IDF has put together a webinar titled The Role of Processing of Dairy Products in Achieving Food Safety and the Science Behind it. For those who are not familiar with the International Dairy Federation, better known as IDF, it is a non-governmental organization founded in 1903 with 40 member countries representing around two-thirds of world's milk production. It engages 1,200 experts from different countries and has been involved in providing science-based evidence and advice for standard and regulation setting. Dairy safety and quality is one of the four pillars in the IDF work areas, the other three being sustainability, standards, and nutrition and health. IDF is the only NGO whose recommendations are distributed by Codex Secretariat as proposed draft standards in respect of milk and milk products. IDF's scientific publications, such as bulletins, fact sheets, and position papers on contemporary issues, constitute one of the most reliable and trusted information sources for the global dairy sector. These can be downloaded or purchased online from the IDF website. Also, you can get in touch with your national committee that represents IDF in your country for more information and also for becoming an IDF expert. So coming back to the webinar today, and we all know that foods are subjected to processing basically for two reasons: for making them suitable to eat, for example, cooking of vegetables, or for making them safe for consumption, such as pasteurization of milk. Well recognized as a near complete food, milk can also be subjected to processing for making many products out of it. In fact, there is probably no basic food that is amenable to processing in so many ways as milk, such as concentration, drying, separation of fat, fermentation, and heat acid coagulation for making different products such as sweetened condensed milks, milk powders, cream, curd, yogurt, cheese, paneer, etc. This webinar will, however, focus on the role of processing in food safety and discuss the science behind it. We have got three distinguished speakers with deep knowledge and extensive experience on food safety. Let us now listen to them. And as for the questions, you can ask questions at the end of each presentation and also at the end of the webinar. You may also share your questions through the chat. We will put them up to the speakers. Your question may not, however, appear in the exact same way as you wrote, because we would try to club related questions. Also, in case there are numerous questions, we may be required to choose. So let us begin. First, I would like to invite Dr. David Everett from New Zealand. Dr. Everett is a food chemist specializing in colloid and surface chemistry in dairy, focusing on how food structure affects flavor, texture, and nutrition. He has led dairy research across 5 countries and holds a PhD from University of Wisconsin-Madison. Currently president-elect of the American Dairy Science Association, he also serves on the editorial board of the Journal of Texture Studies and represents New Zealand in IDF Standing Committee on Dairy Science and Processing Technology. He is a fellow of New Zealand Institute of Food Science and Technology, American Dairy Science Association, and also Food Standards Australia, New Zealand, and is a principal investigator at the Redet Institute. Dr. Everett will speak on history and evolution of heat treatments of milk, demonstrating safety through science. I now welcome Dr. Everett. The floor is yours. Thank you.
Thank you, Adit, for that introduction, and also thank you to the International Dairy Federation for inviting me to give a talk on a very important topic, which is the pasteurization of milk. Before I begin, I'd like to just say that I gave an interview several years ago on a radio station in New Zealand, and the correspondence that came back from the listeners of my talk were rather interesting. There was a certain degree of non-acceptance of any kind of processing, and that they need to be all food that we needed to eat needed to be natural. And I thought that was a rather interesting comment to make because there are things that are natural in the world that will poison us, and things that are processed that will give us nutrition. So at the end of this talk, I hope that you will come away with a message that the processing of milk is very important for not just health, but also nutrition. So I'm going to start out with a history of the process of pasteurization. And I'm going to try and move this next slide forward, and hopefully this will work. I may need some help from somebody to move that slide if it's not moving for me. So the history of thermal processing, and if you could just click for, thank you, right. So Codex Alimentarius has designated, but don't click too quickly, please. Codex Alimentarius has or specified that any raw milk that is heat treated but not beyond 40 degrees Celsius is still regarded as raw milk. And the reason for that is that the amount of heat that's given out is not sufficient to inactivate or kill off significantly some of the pathogens or spoilage organisms that might be present in milk. Next click, please. So the history of heat processing started back with Nicolas Appert from France. And in 1810, he developed the large-scale processing of in-can sterilization. So basically that was sealed off to the open air in some container, put into boiling water, and for a period of time it was heated and effectively sterilized the food product. No doubt people in their homes were doing this prior to 1810, but Nicolas Appert was the first one to develop this on a large scale. So the next step in the process was from Louis Pasteur, also from France, and he's known through the term pasteurization, but his original work was not in milk. It was in the heat treatment of wine and beer to try and preserve it, and so it didn't spoil as rapidly if it wasn't heat treated. Following on from Louis Pasteur, we have Franz von Soxhlet, and from Germany, and in 1886 he took this process and developed it for milk to make it shelf stable over a period of time. And following from that, Milton Rosenau from the United States in 1912 developed a new process using a lower temperature with a longer time of pasteurization. And the reason that was invented was that the high heat treatment that occurs during pasteurization can have some effects on the flavor, not a lot, but there are some heat-induced effects. The low temperature, long time pasteurization was also a simpler process to use in dairy factories 100 or so years ago, whereas the pasteurization technique of a higher temperature for a very short time was more difficult to engineer. So the history of pasteurization, there's a milk pasteurizer on the left there. This is a plate heat exchanger. And there's a countercurrent flow. On one side of the place, we have the milk going in one direction. On the other side, we have hot water or steam going in the other direction. And so the heat transfer through those metal plates is going to heat the milk to the desired temperature, and then it exits the pasteurizer at a cooler temperature, and then it's rapidly cooled down to something like 4 degrees. So now the purpose of this was to reduce pathogenic bacteria to an acceptable level. And by acceptable, that means that the milk can be stored for a period of time before consumption and not cause any health issues. And so the standard is a 5-log reduction per organism. Originally, it was developed for Microbacterium tuberculosis and Coxiella burnettii for that 5-log reduction. And Coxiella burnettii is the most heat-stable, non-sporulating milk pathogen that we know about, and it's been implicated in what's known as Q fever, which not a particularly nice disease to have, but it does inflame the inner lining of the heart, and it's fatal if not treated. That's in humans and animals. There was a rapid drop in the incidence of tuberculosis in the first few decades of the 1900s, and we can take that back to the introduction of pasteurization, and more specifically to the inactivation or that 5-log reduction in Mycobacterium tuberculosis. This extends the shelf life of milk from a few hours to a few days up to something like a week or more. And it does this by reducing the number of spoilage organisms, also very importantly of almost eliminating some of the pathogens that are present there. It's very difficult to eliminate 100%, but we get there as close as we can. And also the enzymes that are endogenous to milk. An example of that is lipoprotein lipase, which can induce rancidity through the action on the milk fat. So this extends the shelf life for safety reasons, but also for flavor reasons by inactivating some of those enzymes. And in this pasteurizer, turbulent flow is required, and the mixing that occurs through turbulent flow as opposed to laminar flow enables the efficient heat transfer. So we can heat the milk to whatever temperature we desire for a shorter period of time, which requires less energy if it's in turbulent flow. So moving on to the next slide, and there is something like a 5-second delay between Europe and New Zealand with this clicking. So the heat treatment is an indirect process, as I mentioned before. It needs to be cooled down rapidly, as quickly as possible, down to 4 degrees before it's then packaged as a product. Now, the temperature that's used, the one that's commonly used for continuous pasteurization, is high temperature short time, also abbreviated as HTST. This increases the shelf life of milk by up to about 2 to 3 weeks, depending upon the initial hygienic conditions of the milking. The other way to do it is a simpler way, and that's, I mentioned before, low temperature, long time. And that one's held at a lower temperature for a longer period of time, which is much more easy, as I said before, to engineer the equipment in a small dairy factory to achieve the intended result of inactivation of organisms. With that HTST process, which is very common, we can increase the temperature up a little bit. This is commonly done, HTST, if you look at the graph on the left, at 72 degrees for 15 seconds. Whereas batch or holder pasteurization, which is easy to do, is at 63 degrees for 30 minutes. Now, if you look at the graph there, as you go to higher and higher temperature, you need less and less time to achieve the same inactivation of spoilage and pathogenic bacteria. So at very high temperatures, for example, 90 degrees, very difficult to achieve, but you can do that to heat it for something as very rapidly of 0.1 of a second. But it's, of course, the expense goes up in the dairy equipment for those shorter time periods. So if we take the temperature up from 72 to 72 to 76 for 15 seconds, plus we use a filtration technology and a bacterifugation technology, which means centrifuging it to remove bacteria, and we combine that with very clean packaging, we can get something called an extended shelf life milk product, or ESL. ESL is not tightly defined in legislation around the world, and there's a wide range of temperatures and times that can be used in order to produce ESL milk, but it has a longer shelf life than the continuous HTST pasteurization. Thermization is another way of doing it that is less effective at killing bacterial organisms, but in some cases that might be required, or it might be desirable to use thermized milk for cheeses such as Swiss cheese. In that case, we might use a temperature of 63 to 65 degrees for 15 to 20 seconds, rather than minutes. So less effective, but we get retention of some of the bioactives. They're not inactivated, and some of the enzymes are not inactivated, which are important for cheese ripening. So we can use that thermized milk. And there are other preservative functions in cheese making that mitigate against the lower temperature and the shorter time in thermization. This gives a log 3 to 4 reduction, and it extends the shelf life of milk by about 3 to 4 days compared to HTST. So moving along, there we go. Effectiveness of pasteurization. Now, we'll just get to the first point here, bit by bit. So just a bit of basic microbiology here. The D value of a microorganism is the time required, and this is for individual microorganisms, for a 1 log, which is a 90% reduction, at a specified temperature. The Z value, which is coming up on the second line eventually, of a microorganism is a temperature increase in Celsius required for a 1 log reduction in a D value time. So those are two kinds of parameters that you can use to measure the effectiveness of pasteurization. Now, in the next lines here, inactivation, now these are some pathogens that may or may not be present in milk. But for a 15-second time period, I've got a number of temperatures listed there from 61 up to about 67 degrees. And what we have is D values listed next to the organism. So for example, for Staphylococcus aureus, to get a D value of 6.7, which is a huge reduction in terms of percentage, over 15 seconds, you would need to heat it to 66.5 degrees. So we can get these kind of values from different organisms, and depending upon the prevalence of these pathogenic organisms or spoilage organisms present in milk, we can then apply those values and change our pasteurization conditions or our heat treatment conditions. So the next slide is coming up. Now, how do we measure that? We use a test called the alkaline phosphatase test. And alkaline phosphatase is an enzyme that's endogenous to milk. It's used for the dephosphorylation of proteins. Now, it absorbs to the milk fat globule surface, and I'll talk a little bit later that milk fat actually has a protective effect when you apply heat in terms of the killing power of organisms. This enzyme, I should say, is inactivated at the same time temperature combination as we use to inactivate Coxiella burnetii, which, if you recall, is standard pasteurization conditions of 72 degrees for 15 seconds. Incidentally, in some parts of the world, they do go to 72 degrees for 16 seconds, and I guess that's just to be a little bit on the safe side. This is a simple colorimetric method developed in 1935. It's down to about 0.25% adulteration of raw milk. So it is used to test to see whether milk has been pasteurized or not, but adulteration is also can be detected. The Shiro rapid phosphatase test can detect down to 0.1% adulteration, and those are the standards that have been produced by ISO and IDF. And then we have newer, more sensitive fluorometric tests, which can test down to 0.006% adulteration. And those have been adopted by ISO and IDF as Part 1 and a Part 2 standard. So a very important measurement in order to detect whether pasteurization has occurred. There are other newer non-thermal technologies, and these include high-pressure processing. Now, I have heard, I don't live in Australia, but it is approved for use in Australia as a cold-pressed raw milk, which is interesting. And I guess you have to call it raw milk because it hasn't been heat treated. And of course, the definition of pasteurized or non-raw milk is that it has been heat treated. This is done presumably at cold temperatures and pressed to a very high pressure. And I'm guessing at something like about 600 megapascals. Now compare that to a homogenization in a dairy factory, which is something like 15 to 20 megapascals. So much, much higher. And it basically breaks apart the organism's membranes and kills it. So pasteurization and the shelf life is given on the chart on the table there. We can also use bactivigation to centrifuge out organisms, and with the addition of pasteurization can extend shelf life by 2 to 4 days. We can use a microfiltration technique which filters out the bacteria, plus a high temperature process of cream, and then we can pasteurize that, and that extends it by about 11 days. So the pore size of these filter membranes is about 1.4 micrometers. If we go to a 0.8 micrometer size, we can extend the shelf life by another 20 days compared to pasteurization. And a high temperature treatment, HTT, which has been mentioned already in that table, gives an extension beyond 20 days. So we can get to something like 30 to 40 days plus using those high temperatures. This is bordering on what we term ultra high temperature treatment, UHT, which I'll cover in a few minutes. The other ones are pulsed electric fields, ultrasound, and UV light. UV light's a bit problematic because you need a very thin film of milk in order to inactivate the organisms. Doesn't work with bulk milk particularly well. So pulsed electric field treatment is very interesting. We apply a high electric field to milk, and this is some work that Pankaj Sharma, I've got the reference down the bottom there, a PhD student about 10 years ago, applying this high electric field intense charge, either as an exponential decay pulse or a square wave pulse. And what that does is that beyond a critical value of the electric field intensity, it can break apart the membrane of a cellular organism. And I think what we have there is looks a bit like more like a fat globule, but to pretend it's an organism. And it basically kills off the organism. So a very effective way, but there are some problems with this. The first is that this pilot scale process, we were running at the very slow volume rate of 4.2 milliliters per minute, which is not commercially feasible. There are bigger pieces of equipment now that can get to higher volume rates to process milk. The other issue with pulsed electric fields is that it doesn't particularly work all that well at cold temperatures. So you need to heat the milk, and I'm hoping the next slide is going to come up. We need to heat the milk first. And what we found out, the most effective temperature was to heat the milk at 55 degrees for 24 seconds. And that allowed the pulsed electric fields then to start to inactivate, kill off some of the organisms. So in the first graph there are microbiological effects. On the second are enzymatic effects. So microbiological, of course, is related to food safety. Enzymatic effects is more related to the flavor or the off flavors that are developed as the milk is stored. So we see there we inactivated it with either E. coli, with Listeria innocua, which as the name suggests is rather innocuous. It's not the monotosogenes. We measure total plate count of the inoculated and non-inoculated milk. As the electric field intensity increased from left to right, we see that we get a very significant, in fact, it's basically the elimination to below detection limits of E. coli and L. inocula. And that's at around about 16 kilovolts per centimeter. But we still have the total plate count for both the inoculated and the non-inoculated milk, which slowly decreases as we increase the electric field. Compare that to batch pasteurization, which is the second collection of columns on that left-hand graph, and also the HTSC pasteurization. So we can see there that it basically has a very similar effect, at least for these two organisms, to inactivate them. Now, 55 degrees is a good temperature to use because we don't get inactivation or denaturation of some of the enzymes that may be important in milk, particularly when we use it to make cheese. On the right here, we have two enzymes and lipolysis. And these are relative enzymatic activity on the left. So we have raw milk. And as we increase the electric field intensity, we see there's a rapid drop-off in the extent of lipolysis. We then see a very, or a bit slower decay in xanthine oxidase and plasmin. Now, plasmin is important for cheese ripening, so we may not necessarily want that to occur. And xanthine oxidase is an enzyme that has been implicated in the formation of gout in people, but we do know that it has some relevance in the development of cheese flavor as well. So we don't necessarily want to inactivate or denature those two enzymes. But this illustrates well that pulsed electric fields, if you can get away from the relatively low flow rates and also the expense of the equipment, is a possibility to replace pasteurization at some point in the future, depending upon the application. We'll move on to the next slide. Equivalent pasteurization. This is milk on the left-hand side of the table, less than 10% fat. On the right side, more than 10% fat. And as the time goes up, as we go down the table, we see that require lower temperatures as we apply the heating for a longer time. And this is very important because it's not just the heat that kills the bacteria, it's the heat and time combination that does that. If we have greater than 10% fat, fat has a protective effect to a certain extent. It's not entirely clear from this table, but it does require a longer time in order to pasteurize it. So if you have a cream product, for example, you would pasteurize it either at a higher temperature or for a longer time or both in order to get the same killing power. Sugar also has a protective effect towards microorganism inactivation, and it does that by lowering the water activity. Right, so the next slide is the effect of raw milk adulteration. So this is using an alkaline phosphatase test using a fluorescent method. And as we increase the amount of raw milk to very, very small amounts, it's easily detectable. You see when 0 raw milk is there in whole milk, the value of 12 goes up to 256 with a 0.05, and that's percent adulteration. So it's a very sensitive test. We go across whole milk, skim milk. For chocolate milk, it's similar. As we increase the fat content, though, that has there's a different result that you see there, and you see that it's going to require. It's not as sensitive in order to pick up the same amount of adulteration because of the presence of the cream. So the microbiological effects include, these are things we need to consider when we're making safe dairy products. A healthy herd, hygienic milking, rapid and maintaining cold temperatures post-milking, and reducing post-pasteurization contamination. Absolutely essential for farming practices. Post-contamination, commonly by gram-negative psychotrophs, and these could include Pseudomonas, Aeromonas, and Enterobacteriaceae, and they cause unclean flavors. For a reason that's not clear to me, the contamination in ESL extended shelf life milk is mostly gram-positive contamination. Pathogenic microflora that might be present include the following. The ones that are inactivated by pasteurization here include the sugar toxin producing Escherichia coli and the Listeria monotysogenes. And finally, Microbacterium avium subspecies paratuberculosis is a known causative agent in Johne's disease, which is in cattle, and Crohn's disease in humans. And this organism appears, there's some conflicting results in the literature about this going back a decade or more. In static pasteurization in a lab situation, the organism survives static pasteurization. But there are studies that show that it's inactivated under turbulent factory pasteurization conditions with a 4-log reduction. So again, we appear to be under pasteurization conditions right at the cusp of this being a problem or not a problem. Next slide. Going to sterilization, I'm going to refer to this as commercial sterilization and extended shelf life. So what we have here again is time versus temperature. As we increase the temperature, we can heat it for a shorter period of time to have the same killing effect. So we have two lines here, the B curve and the C curve. The B is referring to biological inactivation. The C is referring to chemical inactivation or destruction, in other words. So for a B star equals 1, that is the blue line, I believe, if I can look at the line down here. And yes, it is. And the orange line is the C line. So for B asterisk equals 1, that's equivalent to 10.1 seconds at 135 degrees Celsius, which is effective commercial sterilization, 9-log reduction. With a C star equals 1, that means a 3% destruction of thiamine, one of the B vitamins. So talking about chemical or vitamin destruction in this case, that's equivalent to 30.5 seconds or 135. And you can see there the in-container sterilization zone, which goes back to Nicolas Appert. And on the right side, you see the UHT zone, where you produce a very shelf-stable milk that can be stored at room temperature. And I'll get to that in a minute. So ultra high temperature UHT, 135 to 150. Lower temperature, 10 seconds. Higher temperature, 1 second. We're looking at about 9 months if we have aseptic packaging. We can extend it beyond that to more than 12 months if we use microfluidization and high pressure processing on top of UHT processing. Now this can be stored at room temperature as long as it's aseptic packaging. For extended shelf life, we have a lower temperature for a little bit longer. It sort of butts up against the UHT region. A long life as for UHT, but less of that cooked flavor, which is due to volatile sulfur compounds from denatured beta-lactoglobulin protein that you may find in UHT milk. Shelf life is less than UHT. We're looking at about 15 to 60 days there. Again, as I said before, ESL is not well defined in the legislations around the world. In container sterilization, by comparison, lower temperature for a much longer period of time. And that's, again, what we refer to as commercially sterile. Now, the two kinds of UHT methods are indirect and direct. So with indirect, it's basically it's a heat exchange process. So it takes a lot longer to get to that temperature, 140 degrees. At that point, it's spent so long getting to that temperature, you can start the cool down process pretty much immediately. Some of the UHT issues include stale oxidized flavors, chemical reactions during storage, age gelation due to heat-resistant bacterial growth. The other method is a direct UHT commercial sterilization, and that should be appearing. What we see there is this may be a steam injection system. So the temperature goes up to an initial plateau of about 90, and then you can sharply increase the temperature very rapidly to 140. And then by releasing the pressure, you can get a cooling effect occurring, which takes the temperature rapidly down to about 90, and then slowly cool it down to room temperature and refrigeration temperatures. So two different ways of doing that, and both have pluses and minuses. So moving on to the final slide, nutritional effects. This is good news to those radio listeners I alluded to before who thought that the nutrition was taken away from pasteurized milk. No substantial effect on milk fatty acid profile. Little effect on proteins. Pasteurization, 72 for 15 seconds. We get 5% denaturation of globular whey proteins. That is more of a textural functional issue. And it has some digestibility issues as well. It makes it more digestible. A tiny little bit, probably not significantly different. None for thermized milk in terms of proteins. Higher degree of denaturation for ESL and 100% for in-container sterilization, plus some browning reactions due to the Maillard reaction, which causes a discoloration or a browning of UHT milk. Very small reduction of the essential limiting lysine amino acid. Not really a problem, 1 to 4%. I guess you just have to drink 1 to 4% more of the milk. 7 to 10% loss in B12, less than 10% for the other B vitamins. But pasteurized milk is still a very good source of the B vitamins. So the heat has almost no effect there. It does have a more significant effect on vitamin C, but you would not be drinking milk as a primary source of vitamin C. You'd be eating fruit. No effect on the fat-soluble vitamins A, D, E, and K. And oligosaccharides. Now, these are important for stopping adhesion of pathogenic organisms to the epithelium. In other words, the lining of your intestines. These are heat stable, so that's good. They still maintain their activity against pathogenic infection. And antimicrobial proteins, lactoferrin, lysozyme, listed twice. Minimally or not affected, but lactoperoxidase, which is required, I believe, in Switzerland, loses about 30% of the activity. Lactoperoxidase is antimicrobial protein. It's inactivated by what's known as the hydrogen peroxide thiocyanate process. So I think our last point, calcium bioavailability, very interesting point. Heat does nothing to calcium. It does make calcium phosphate more insoluble, and it's already insoluble to a large extent within the casein micellar milk. The form of calcium is the thing that dictates its bioavailability. So what type of calcium phosphate it is, whether it's calcium carbonate, whether it's calcium gluconate, different things like that, that's irrelevant to pasteurization. It's really has no effect at all. So that is all I'm going to say about the safety of milk. So thank you, and I will hand back to the moderator.
Thank you, David. You spoke about history of heat treatment and how it came to be applied to milk. You also talked about the two types of classical heat treatments, that is low temperature, low time, and high temperature, short time pasteurization methods. You talked about extended shelf life milk, thermization, and also the utilization of alkaline phosphatase test for checking the efficiency of pasteurization as well as its sensitivity in different products. You also talked about the newer methods of processing of milk for making it safe, such as pulsed electric field method, high pressure method, their equivalence to pasteurization, and also about the commercial sterilization using UHT in container sterilization. And you also talked about the impact of these heat treatments, specifically pasteurization, which is very commonly used heat treatment for making milk safe and extending its shelf life to some extent on the nutritional value of this treatment. So a very well presented, very streamlined, very focused presentation. And thank you so much for your presentation. So second, I think uh, we have some question and answer time to your presentation. There's a term that you used, Dr. Everett, called commercial sterility. So, what actually is commercial sterility? Can you just elaborate a little bit more on that?
Yeah, very briefly, commercial sterilization is not the same as complete sterilization. And we don't actually achieve complete sterilization because there's always going to be a few pathogens floating around there. But the important thing to remember is that commercial sterilization lowers the number of pathogens to such a degree that they don't grow to become a health issue. So that's what we mean by commercial sterilization.
Thank you, Dr. Everett. I think it's a very nice concept that you don't sterilize it fully and sterilize it only to the extent necessary, I would say, to make it safe in practical terms. So, with no more questions at this time, I would like to invite the next speaker, and maybe we'll take some other questions for Dr. David. If you have viewers, we can take them at the end of the webinar. So we move on to the next speaker. I now invite Dr. François Bourdichon from France. Dr. Bourdichon is chair of the IDF Standing Committee on Food Hygiene. He holds degrees in microbiology from the Pasteur Institute and Università Cattolica del Sacro Cuore. With 15 years in major food companies including Nestlé, Danone, Savencia, Barry Callebaut, he has worked since 2017 as a food safety and hygiene consultant and since 2022 as a scientific collaborator at Università Cattolica. He has represented France at International Dairy Federation since 2010. He chairs the IDF Standing Committee on Food Hygiene and contributes to ISO working groups on dairy microbiology. He is currently Director of Laboratory Methods and Microbiology at Sodial. Dr. Bourdichon will speak on microbial monitoring in a cheese processing environment. Welcome, Dr. Bourdichon. The floor is yours.
Thank you, Aditya. Hello, everyone. So following the presentation of David, it's important to emphasize that we wanted milk to be safe, hence we put some control measures in place in order to ensure the safety and the longer shelf life of the milk. Having said that, we discovered as well that even so we work with a safe food matrix from the start, there might be still some contamination occurring in the next steps. And that's precisely the topic of my talk now, is what we do in terms of microbial monitoring in the processing environment with a focus on cheese and on Listeria monocytogenes. So there is a little bit of shift. Yeah. So the issue in microbiology is that it's very difficult to detect low-level contamination, and there are expectations from the consumer sides to really ensure a safe food. And this is an extract from an outbreak to milk powder that linked to salmonella, and that's not the topic of today, but it's important to emphasize that routine microbiological controls are not sufficient to detect low-grade contamination. This is emphasized in the ISO wording of microbial method from the ISO TC34 SC9. We used to mention in the standards absence presence, which was misleading. And now the wording is detected, not detected, not detected or detected, because the methods might not be efficient, and also because in the sample, you might not have the contaminants. Does not mean that in the whole batch, there ain't something. So there is always a limit to microbial testing, and you cannot put everything on finished product testing to ensure the safety of your process, which is per se not something new. We often refer to a study from Abraken and al. What's not moving? Okay, study from 1986 for the management of salmonella risk. And again, the introduction starts with mentioning that there's a lack of friability of mere examination of finished product. And this is valid for whatever process you have in place. If you test, you're only as good as the sampling approach that you've done, and you cannot rely on everything. Having said that, it's important to react before it's too late. And I take this very example, tracing back to 2021 on queso fresco, where the facility knew that there was some Listeria SPP in the processing environment and did not react properly, made things but not properly, and it ended up some months after with an outbreak of Listeria and a death people. And this is something we mentioned in the 2009 IDF bulletin on Listeria SPP and Listeria monocytogenes in the dairy chain. It's important to look in the processing environment for Listeria monocytogenes when it comes to cheese productions, because it's a wet and chill environment. And it's important to use as an indicator Listeria SPP, the whole genus, not any other microorganism. Listeria SPP is a good indicator of the potential of your processing environment to be fit for purpose for Listeria monocytogenes. And in terms of ecological competitors within the genus of Listeria, they have species far more efficient, if I might say it so, than Listeria monocytogenes. So it's important when you monitor to look for the genus, and if you do not have the pathogenic species, you're safe for now, but you're still in trouble because it means that it might come at some point. So it's important to react properly. And in a processing environment, we have this concept of the product proximity, making a distinction between food contact surface and non-food contact surface. This is what you might find in Codex Alimentarius documents on food hygiene. And there is also a distinction on non-food contact surfaces with 3 levels. 2 are referring to non-food contact surfaces in close proximity to the food contacts and in the processing environment. It's either called zone 2 or zone 3, or on some guidelines E1 or E2, and zone 4 or E3 is outside the processing environment. This is where it's important, because in terms of ecology, we discover that in pasteurized or heat-treated milk product, when we produce cheese, the Listeria we might find at some point in the product is coming from the environment. It's not coming from the matrix, because as David precisely mentioned, through the pasteurization step, if it's properly done, you don't find any Listeria anymore. So if you end up in your pasteurized milk product with a Listeria on your product, you have a contamination from the processing environment. This is not something new per se. It's concept of the proximity approach, which pushed in the early 2000s by the ICMSF, the International Commission of Microbial Specifications in Foods. It's been adopted in the United States and it's highly promoted by the US FDA. It's a mandatory requirement. Per se, in Europe, we are not there yet. We have guidelines from the reference laboratory for Listeria where this proximity approach is not mentioned. There is no distinction between food contact and non-food contact surface. And presently in Europe, we've got two unions proposing the approach. One is Prof for frozen vegetables, and the other one is FEVIA for the Belgian food industry. And it's important when you monitor for the environment to know where you monitor and how you clean. And there is often, unfortunately, a misunderstanding between processing environment monitoring and cleaning monitoring. It's not the same. If you make the swabbing after cleaning, you're just monitoring if you clean properly. You have no idea about the environment. And it's mentioned in many guidelines on processing environment monitoring. It has to be done during the shift of production or at the end of productions. And there are some devices which are meant for cleaning monitoring, and you find them in environment guidelines. It's not appropriate. Cleaning monitoring is not processing environment monitoring. But what is important is to have this, to be aware that in order to have a monitoring of the processing environment, you need to have everything in place, the PRPOs, which means the hygienic zoning, the cleaning must be in place, and also the good manufacturing practices. And it's important whenever you are somewhere in your facility to know what's the hygienic zoning level, which is the type of cleaning practices I do have in place, and what's my proximity with the food contact surface. So we have a regulatory framework in Europe since 2005. It was mentioned in the Warehouse 22 that it's important to monitor the production and processing environment. Nevertheless, in 2005, quite interesting, we didn't have the standard for swabbing. We had only technical specifications. And only in Article 5 was mentioned that you should, at the ready-to-eat food business operators, monitor for Listeria monocytogenes. So not the genus, but the species per se. And something which was wrong, and even so it's in regulation, sometimes it's wrong from a scientific perspective. It was mentioned that you should monitor at the food business operators in infant formula for Enterobacteriaceae, which is hygiene monitoring. And in case of deviations, look for Enterobacteriaceae and Enterobacter sakazaki, which now is nomenclatured as Chronobacter. They made an amendment, luckily, in the 2007 regulation, mentioning that there is no correlation between hygienic monitoring for Enterobacteriaceae and Salmonella monitoring as pathogen of concern, and that you should prove if there is a correlation between Enterobacteriaceae and Chronobacter SPP. And we know it's not there. And why do we have this clear separation between hygienic monitoring and pathogen monitoring? Because there is always a request from some players in the industry to say, I'm performing my hygiene, I have hygienic indicators, and in case of concern, I'm looking for pathogen of concern. The point is, this is wrong. There is no clear correlation between hygienic monitoring on one side and pathogen monitoring on the other. And when you refer to processing environment monitoring, you need to refer to both. Why? Because of the concept of resident and transient strain. This is a concern which is known and adopted for more than 30 years in the food industry. And there were some academic studies that started in the early 2000s on this one. I'm sitting here, one of the oldest publication I could find on Listeria monocytogenes. It's not related to cheese. That doesn't mean it's not valid. They mentioned that Listeria bacteria could be part of the resident flora of the processing environment. And this is something to have in mind. We do not work in sterile environment. It's not possible. And if you have a cheese factory, even so it's very well designed and you have everything in place, it's potentially an ecological niche for Listeria SPP and at worst for Listeria monocytogenes. So even if you design it very well, you need to make sure and monitor that everything is going as expected and there isn't any breach in the approach. We only had recently a publication from a European Food Safety Authority earlier last year about the persistence of microbial hazards in food and feed production and processing environments. So this publication is very important. As for the food industry, it's only confirming something we knew but never worked on publicly, because we are not academic people, we are shop floor people. But having this understood and agreed upon by the European Food Safety Authority is also very important for each company working within the European context, to explain that we do not have a sterile environment, we're doing our best, and we know where it is, and we are tackling these different niches to make sure that there is as low possibilities of survival of the pathogen of concern as possible. But sometimes when you hear people say, we want to work in listeria-free facilities or salmonella-free facilities, they are not per se listeria-free. They are free as much as you can see and the best you can do, but to ensure a sterile environment, it's not possible. What is microbial persistence? And it was the proposal from European Food Safety Authority is to mention that the strain is present in what we call harborage niches. This is the wording also we do have in Codex Alimentarius guidelines. The IDF worked some years ago with my colleague, former colleague Klaus Egum from Denmark and myself on the annex on the code of hygienic of low moisture food, and we mentioning the processing environment monitoring and hygienic indicators Enterobacteriaceae and Salmonella for this specific environment. And a resident strain can be detected through repeated isolations at the same premises on different dates, and it can survive for a very long time. We have records either with Salmonella or with Listeria cheese of strain which through whole genome sequencing we can see has been present in facility for 5, 10, 15, even 20 years, depending how far we can trace back in collection and finding isolates. So unfortunately, it does happen. What is important is to have monitoring of your environment to make sure that at least in the food contact surface and in the care environment where you need to be careful for the product, it's not present, but it's somewhere and you're tracking it. So why do we do this? Because there is a regulatory framework, as an example, from the EU regulation 2073, so for more than 20 years now. We have a standard, ISO 18593, which was updated in 2018. It's a typo here. We have this EFSA opinion that mentions we have microbial and microbial persistence in the environment. Now, where do we sample? That's the tricky questions you often get when you go in facilities. You say, okay, nice page. Where do I sample? And here you've got the definition providing from a technical assistance from EFSA. The relevant critical sampling sites can be defined based upon critical inspection. Let's face it, that's not very helping. Indeed, you need critical inspection. Now, how do you perform the critical inspection? How do you look? And this is where sometimes you have the microbiologist entering the facility and say, you should look here, here, and here. Sometimes you find, sometimes you don't. How do you do? I don't know. So what we try to do in the action team within the Standing Committee on Food Hygiene is try to be clever and understand what the rationale, what we are looking for, how do we decide which sampling sites do make sense. First thing is, not all samples are the same. We need to define routine sampling points, which will be like the guardians. But not focus too much on this one, because they are only as good as you think they are, and they might give you a false inspiration. This is why it's important to have also as well investigation sampling points. When people are going on the shop floor for the swabbing, they've got like 15 swabs already for defined points, and you can perform trend analysis on this one. And they've got 5 to 10 extra swabs. If anything fishy, not good, then might be important to have the swabbing. And if you find there, that's good investigation. So that's its abnormal conditions. In case of special events, if you have maintenance, repair, constructions, we are not very comfortable when the processing guys come and say, we need to replace the coagulator, we need to replace places in the room, and we bring in new equipment, which means machines, wheels with dirt from the telluric microorganisms, Listeria entering the facility. So it's important to monitor any disturbance, to anticipate, and to prove that after the work, after the repair or whatever maintenance has been done, things are back under control. And because sometimes you need additional samples after following a detection of positive results in order to investigate better. This is what in the US FDA guidelines are mentioned as vector samples. So you often find in processing environment the search and destroy approach. Fine, this is investigation. When you search and destroy, you're not searching and destroy the gene, the isolates, the strains. You're searching and destroying harborage niches where it might be present. This is mentioned in the EFSA publication when they mention what are the common risk factors for persistence in the food and feed processing environments. Inadequate zoning and hygienic barriers. So if you poorly design the flows within your facility and people can enter too easily, they come also as well with little contaminants from the external part. It depends also on the design of your equipment and machines. So hygienic design is very important to make sure that you have an hygienic process. Having said that, hygienic design is already 30 years old, but still it's not, it's an approach that was implemented with equipment that are older than hygienic design approach, so there is some retrofit needed. It's important to have the proper cleaning and disinfection. In the code of hygiene of the codex, it's mentioned cleaning. The distinction between dry, wet, and controlled wet cleaning is only mentioned in one codex guideline, the Code of Hygienic Practice for Low Moisture Food. But depending where you are, you do not clean the same way. Cheese facilities, it's wet cleaning, eventually controlled wet. It's not dry cleaning. Reversely, in milk powder, which is not the topic of today, it's dry cleaning. So if you don't have the appropriate cleaning practices, you don't end up where you want to be. And it's important also because it's not all about milk. You've got different sources about the introduction through raw materials. And there were all guidelines on HACCP in the 90s mentioning that some raw materials should consider as critical control points because they are introduced after the heat process. And if they are contaminated, you contaminate the finished product and your global process. Going to go to the next one. Okay, so what are the threats? The microorganism of concern, a potential harborageness, the water activity where you're located, and if you got food, organic matter. Which means that how do you control it? Through hygienic zoning, hygienic design to make sure that there is no niches where the isolates can survive. You need to have dry cleaning, control wet whenever it's possible, and if it's needed. In cheese facility, it's mostly wet, and need to hunt for leaks. If you've got organic matter dropping down on the floor, this is food for the bugs, which is very complicated in the cheese, particularly in the ripening zones, because by design, everything is contaminated somehow by organic matter. So once you combine, the hygienic zoning is a way to ensure that the microorganism will not enter the facility. The hygienic design is a way to make sure that you won't have place for survive for the microorganisms. If you hunt for every leaks or raw mat or shop on the floor, whatever, in order to ensure there isn't any food for the bugs, that's another way. And then depending on which type of clean you have in place, and if you have water leaks, if you've got near the drains, the water is flowing and you do not have enough evacuation of the water, that's not good. It's mentioned in the 2019 guidelines from Bulletin, from the IDF on Listeria SPP and Listeria monocytogenes. When you have a detection in the drain, is it because the drain has been contaminated or it's a contaminant? It depends. And after the questions, where do I swab? Usually it's how many swabbing points per week do we have? In microbiology, most of the time, the answer is neither yes or no. It depends. It's always a case-by-case assessment. You can have a very, very big factory, very well designed and closed process, very small points. You can have a small old factory, poorly designed, with poor practices in place, many, many points. So there was an attempt from the team of Martin Wittmann from Cornell University to propose a way to define the number of swabbing points. It's a good approach. It needs to be to face reality of the field, because not all cheese facilities will require the same number of swabbing points per week. As a conclusion on the processing environment, which are the countermeasures that should be implemented in the facilities in order to ensure a safe food and feed processing environment? First is to focus on the hygienic design. and eventually some retrofit with the operation. If you know that one of the equipment is regularly contaminated and is an issue, like a packaging material or a robot whatsoever, maybe it's time to upgrade it a little bit eventually and to change it. You need to have hygienic zoning in place. It's a requirement in the regulation in most food safety management systems, but it just say you need appropriate zoning and get with it. So first thing is redefine workflows. What is very important is all the zoning is based on the hydraulic plan. So it's important not to underestimate the critical role of the air handling unit. Recently had a webinar on EH on clean air for clean products. And we don't have very good guidelines, let's face it, when it comes to hydraulic plants for the food industry, but we've got good guidelines from the pharma. This is where there is some upgrades needed, and hopefully we will cover this in the IDF bulletin on processing environment. It's important for the cleaning and disinfection to make sure it's appropriate. You need to challenge the status quo. We have no ways to get more insights from microbial isolates and see why they might be surviving. And I don't have time to go into the details, but we see we have seen a rise in the recent years of benzalkonium resistance isolates of Listeria while we were using extensively quaternary ammonium compounds. There is clearly a correlation and a causation because of this. So it's important when you've got a persistent strain to look into detail why is this strain persisting environment, and sometimes it's because it has been selected through the cleaning. And that's the tricky point with Listeria. If you don't clean, you have it. If you clean, you have some of them. So it's important to make sure that your cleaning and disinfection is done appropriately. Rotation, if can be done with the equipment, and the appropriate routine cleaning scheme. Raw material segregation definitely is a must. When you have the raw milk receptions, it should be separated from the rest of the processing environment, and people in the raw milk reception should not enter freely in the cheese facility. And as well, process leaks. So always the questions, how should we clean? First, don't mess up and don't get dirt on the floor. And to open the discussion, we have now in Europe an alignment with the practices in place in the United States, hence the support from the Food and Drug Agency to the working groups, that we are building a database in EFSA, European Food Safety Authority, on food isolates. The European CDC in Sweden has a collection of clinical isolates, and we can make through whole genome sequencing comparison, a correlation between the two. Now, this is something we already mentioned at the IDF level in the 2019 fact sheet on whole genome sequencing, which was done by the Standing Committee on Microbial Hygiene. Whole genome sequencing is very helpful. Now, what is important is to have the right epidemiological approach. As an example, Listeria monocytogenes ST6 was the same strain type between the South African outbreaks on deli meat and the Hungarian outbreaks on frozen vegetables, not correlated. So when you have clinical isolates, sure, there is a hint that it might come from these different food zones. Then it's important to go more in details and to make sure that indeed there was consumption on the food, and we can conclude indeed which food facilities is responsible for the ongoing outbreak. And concluding the word of Louis Pasteur, it's a tough world we're living in, and microbes will have the last word. And I hand the floor to you, Aditya.
Thank you, Dr. Bourdichon, for a very enlightening presentation. You talked about salmonella in infant formula and how the testing cannot always detect it, and the significance of such scenarios. You also talked about presence of Listeria and the fact that pasteurization kills it, and also the fact that there could be post-pasteurization contamination of it, and hence you need to be always in the monitoring mode to be able to take action in time. You also talked about very important concept of product proximity to food contact surfaces, the concept of zoning, cleaning, proximity, and their correlation with the other important control measures. You also highlighted that there may not be any correlation with certain indicators, organisms that we test in routine, such as Enterobacteriaceae, and we take it for granted sometimes that this indicator organism will give us information about presence of pathogens like Salmonella and Enterobacter sakazaki, which may not be the case always. So we need to be cautious on that front. You also talked about the concept of resident and transient strains that harbor in processing environment, and the importance of these phenomena in respect of food safety, the persistence of microorganisms in food and feed manufacturing environments, and that it is not possible to get sterile environment, and then how to address such a scenario to ensure food safety. You also talked about the importance of sampling sites and indicated that not all the samples are same. So it becomes very important to choose the sampling sites to be able to know appropriate measures to ensure and achieve the objectives of controlling the hazards. A very interesting, piece of thread of a sort of communication that you used in one of your slides was keep calm, search and destroy. That sums up sort of entire action plan in very, very simple words. You also talked about common risk factors, threats and control measures, and their integration. How to do it, where to monitor, and what are the caveats. Very practical insights indeed, very useful points coming out of your vast experience. You also talked about equipment rotation and routine cleaning. Thank you, Dr. Bourdichon, for very enlightening presentation. Now, if you allow, I may ask one question, and then maybe if we have more questions at the end of the webinar, we will take. So I'll take at least two questions now. One is you talked about Listeria monocytogenes as a key pathogen of concern in cheese processing. Are there any other microorganisms of concern in cheese processing environment that one should be careful of?
So for the time being, in terms of pathogen of concern, the only one we clearly understand as being relevant is Listeria spp and Listeria monocytogenes. Sometimes we have a discussion in speaking at the French, from the raw milk cheeses, and we get challenged why we are not monitoring for Salmonella in the environment. Now, Salmonella in raw milk cheeses only comes from the raw milk matrix. That is not fit for purpose. The environment is not fit for purpose for Salmonella. Salmonella likes to, if I may say, likes to survive in hot and dry environment. So the cheese processing environment is not fit for purpose. So for the time being, the only one which is of concern for us is Listeria spp and Listeria monocytogenes. There are some comparison in the pharma when they are monitoring for Bacillus cereus. But when it comes to Bacillus cereus, again, in the processing environment, that's not relevant. There are other sources by far more concerning to tackle this contaminant. So for the moment, the only one identified and in part in the regulation is Listeria monocytogenes with a monitoring on the genus in order to be more proactive.
Thank you, Dr. Bourdichon. We have one question from one of our viewers coming up in the chat. What impact do you expect of the update of 2073/2005 with respect to Listeria to become effective in July 2026 in EU?
So this regulation in Europe is meant on the finished product in order to make the distinction between capacity of growth or not. It's coming from a legal issue that we have in Nordic member states some years ago. And now it's the responsibility of the authorities to agree and make the classification where it's growth or growth. When it comes to the food processing environment, that's not changing the deal because you don't want to have it. It will not change the need to monitor in the processing environment. It's a margin which is given only in Europe to accept for products where growth is not expected, not to have a limit of not detecting 25 grams but less than 100 CFU per gram. Nevertheless, you still need to monitor in the environment. Now, specifically for your finished product, you may come with a dossier, first with predictive modeling and then with challenge testing in order to get approval from your local authorities, and indeed there is no growth in your product, and as such you can use the classification 1.3 of the 2073 SALS 2005 regulation.
Thank you, Dr. Bourdichon. And you also talked about whole genome sequencing and its importance in solving outbreaks. So, do you think it will be useful for the industry to adopt such modern techniques, and they may require some kind of expertise? Would
I
you?
do.
Yeah.
First thing is I do, and we are working with different food companies in order to evangelize the use of whole genome sequencing for source tracking. It's very important in understanding why you do have resident strains in your environment to beyond just making the sequencing for comparison with food and clinical isolates, to go deeper in the genome and understand, are there some specific genes that might explain why there is a specific behavior of the isolate that makes it survive. And I took this example coming from a Safe Food 360 project from Ireland, where they have seen a rise in Ireland at the clinical stage of Listeria isolates resistance to basialconium. And we have been using for years quaternary ammonium compounds, and basialconium is a quaternary ammonium compounds. So we have this clear correlation. It's important then, if I only have acidic cleaning and I'm selecting a strain which will survive acidic conditions, so I will need somehow a rotation with basic cleaning. So this is where it's important to also have a liaison with cleaning companies, which are the expertise of which agents might be more relevant, and the equipment designers, because you cannot clean every equipment with everything. Right now, dry steam is becoming a very interesting approach for cleaning, but dry steam cannot be used with every equipment. So it's always a work at three parties between the expectation from the food business operators, the capacity from the equipment, and what's the cleaning solutions are offering. And whole genome sequencing helps you provide more insights why my strain is persistent.
So thank you, Dr. Bourdichon. I think there are other questions, but in the interest of time, right now I would like to move ahead, and maybe if the time permits, we'll take other questions at the end of the webinar. So finally, I would like to invite Dr. Bipan Bansal from New Zealand. Dr. Bansal is Water Resources Manager at Fonterra, leading water sustainability efforts to reduce company's footprint while also ensuring supply security and compliance. He collaborates across sectors to develop safe, sustainable water use and reuse strategies. With broad experience in business, academia, and research and development, he also engages in community initiatives to foster teamwork and social impact. He is also co-action team leader of the IDF work on water use and reuse. Dr. Bansal will speak on processing with safety and sustainability in mind, use and reuse of water, which is a very important topic. Water is a scarce resource. So welcome, Dr. Bansal. The floor is yours.
Thank you, Aditya, for the introduction. It's my privilege to be here. Hello, everybody. Over the next 20 minutes or so, or whatever the time permit, I'll take you through and demonstrate the importance of water in dairy processing. And as a dairy manufacturer, I will also show what we do to ensure that water is safe to use in dairy processing. And when we talk of sustainable operations, what does that mean? I'll see if the slide moves. Maybe oral. Yep, thank you. I have divided the presentation in 4 parts. I'll start with high-level work, what we are doing in the Codex and IDF area around the regulations for water use and reuse and the guidelines. And then go into some details of the importance of water and try to look into it from a manufacturer's point of view and try to cover different angles, which include food safety, food quality, processing constraints. Then we will talk about challenges on water security, water procurement, and complexities around the treatment of water, which is fit for purpose in end applications. And then I'll spend some time with examples on water use and reuse. We'll start with Codex and IDF work. Under the Codex Committee on Food Hygiene, we have been working for over 4 years now. We have developed a guideline. As I must say, this is the international guideline, the first for the safe use and reuse of water in food production and processing. So it covers all areas of food production, and dairy is a subpart of it. This guideline was published 2 years ago. And for dairy sector, we got 2 annexures. The first one is called Annexure 3, which goes into the details of what are the different aspects of safe use and reuse of water, different processes, risks we need to be aware of. And this annexure is ready. It is about to be published. And the last annexure is, which is Annexure 4, which is looking into technologies, food safety approach, water fit for purpose assessment, etc. A lot of work has been done around it. And if you look at the bottom of the slide, going forward, electronic working group will look into it, and then it will be circulated to different member countries. We'll look into their comments, and we hope to get this done within next 1 year. And we are also working on, if it moves, on a bulletin for IDF bulletin. Maybe orally you could help it. Go to next slide, please. The scope of that bulletin will be water use and reuse. And here we'll be starting from dairy farm, but we will be excluding water consumed by dairy animals, but all the processes on a dairy farm, then around milk collection and transport through to dairy processing. So basically we'll be covering the entire sector. We will be looking into water usage, facts and figures. What are the underlying guidelines and legislative requirements? But a key part will be technical details around it. And this will be covered in 3 sections: dairy farms, collection and transport, and finally into processing. Next. Yep. So now look into role of water in dairy processing. Next slide, please. Let's look at from a dairy processors point of view. Like I'm from New Zealand, and Fonterra Cooperative Group, we got some large factories there. The key driver is to turn that milk into milk products for our customers. And water is an enabler. So first and foremost is, do we have sufficient water available to us during processing to turn that milk into milk products? And number 2, do we have enough water to make the products we want to make, whether it is milk powder, whether it is milk protein concentrates, whey protein concentrates, cheese or casein. And the common wisdom is the amount of water required as you move towards value-add products, the water needs increase dramatically. Milk powder generally requires a lot less water than, let's say, cheese production. And number 2 is, do we have water available that is of sufficient quality or adequate quality that every gram of product we are making is safe? And the last one, we talk about whether our operations are sustainable. Next slide, please. Yep. When we talk of sustainable operations, there are 2 aspects to it. The first aspect is, when we talk of water, we need to look across the entire spectrum. When I'm talking about spectrum of water, I'm talking right from the moment we take water into our factories, and then we treat it. Then we look into most efficient use of water, either through water reduction practices or through water reuse. And when water becomes wastewater, how we treat it and how we discharge it. For me, water and sustainable operations, we talk about holistic sustainability. We start from the bottom. Is the footprint the lowest, as low as practically possible? And the solutions we have in place, are they acceptable to the society and the communities we operate in? And what's the impact on the bottom line? Of course, all these initiatives, they require some money. And then the top one is the solutions we are putting forward, are they technically sustainable? Because generally the solutions we need, they need to be lasting for the next 5, 10, 20 years. And these are for the life of the given equipment. So now we look into next section around the challenges around water procurement and treatment. It is a multifaceted approach. First thing is there enough water available in that region where the dairy factory is? Whether the water comes from the local municipal or the council, whether we are taking it from river, groundwater. Number two, what is the quality of that water and what kind of treatment is required? And depending on the source of that water, what's the impact on your plant? If the water is very hard and if you don't have sufficient treatment, it can lead to pitting corrosion. And finally, what's the impact on wastewater? This is here you close the loop. Yes, there may be more water available, but every drop of water you bring in, ultimately it becomes wastewater, which you need to treat and discharge back into the environment. And then underlying principles for all these is food safety and quality is paramount. And then people's health and safety, because when you talk of disinfection processes, whether it is chlorine, whether it is ozone or some other disinfectants, are they safe? And when I'm talking about safety, it is you're looking into not just necessarily from product point of view, from people point of view, and the whole environment around it. And also impact on the overall environment. And probably last but not the least, probably what does my customer want? What are their requirements? That drives a lot of decisions for how we operate in the water space. Next slide, please. Now we look into water treatment and disinfection. Look, it is important depending on where we get the water from. If it is a surface water source, obviously there will be a lot of impurities, physical, chemical, and microbiological. The first step is how do you remove those contaminants? And then how do you do the disinfection? The simplest method is use of chlorination process. And depending on your contaminants and the need for how much chlorine you need to add, there is a fine balance. Means ultimately you are chasing chlorine disinfection and you're also looking for residual disinfectant in water. So the water remains microbial free as it moves into the distribution network throughout the factory. It is important to realize that how do you weigh between the impact of chemical contaminants versus disinfection byproducts? So if we have organics coming along and we keep on adding chlorine, you are going to get formation of byproducts. Some of them can be carcinogenic in reaction. So it is important to know that, yes, chemical contamination is critical, but not at the expense of microbial contamination. Because microbial contamination can lead to acute sickness and illnesses, and it could cause some serious damage to people who end up consuming those dairy products. So if you look into our WHO guidelines, It is clearly mentioned disinfection should not be compromised in attempting to control disinfection byproducts. But this also doesn't say that you do not have to observe due diligence. So if your chlorine requirements go up, please consider, instead of just keep on increasing the chlorine level, what is driving that? Why there are increased contaminants coming through? What's the source of that contaminant? What's the nature of that contaminant? It's important to do root cause analysis. Next slide, please. Now I go into the last sections around water use and reuse. It's a very simple strategy we have been using for 15 years, and it is as valid today as it was then. First one is reduce the use of water. Basically, turn off the tap if you don't need water. In simple terms, do you have leaks in your factories? You got running hoses? You got overflows, poor design? Try to address that issue. And number two, is there any opportunity to reuse water? And if you can do it without treatment, that's brilliant. But if you need some kind of chemical and physical treatment, that will come next. And last, the number four is, if you have got some water that can be reused, you make sure you don't waste it. You utilize every drop of it. And the last one, number five, is if you have no option but to sink in some capital and spend some money, that will be the last resort. Because many times, adding new equipment or new plant may not solve your problem if it is not addressing the right problem. It may end up causing more problem. So look through this hierarchy, and as I said, it has served us very well. Now I'll go into one example. Next slide, please. Before I go in, I'll explain in terms of reused water, reclaimed water. This is the water which is reclaimed from milk, either through milk evaporation process. Some people call it cow water. Scientifically, it's evaporated condensate, or it is through membrane concentration process. Your starting product could be milk or whey. So are you making cheese? You're making casein, MPCs, WPCs. You have streams where the first step is ultrafiltration, then it could be reverse osmosis, or it could also be there is a second reverse osmosis polisher in place. So you got your RO permeate or RO polisher permeate. These are very high quality water streams, which should be we making the best use of. And next slide, please. And here the example will be when you are reusing reclaimed water. Where do you want to use this? What's the end use application? Is it in the direct product contact? Are you using a final rinse water? Is it for ingredient makeup? Or is it around intermediate rinses? Or it is for external tanker wash or for heating and cooling? This will decide what kind of treatment do you need for that water. And if you need to store that water, that also adds further complications and may increase the level of treatment required. Basically, in this case, what we are primarily targeting is the microbial growth, the biofilm formation, what's the potential. Next one. And here is a factory. This is an example from New Zealand, a small dairy factory where we got 2 milk powder dryers. And we were processing around 1.4 million liters of milk per day. This is raw milk. And we needed up to 1.7 million liters per day of water. It's quite an old plant, around 30 to 40 years old. And then around 10 years ago, we needed to expand that factory. We brought in a new dryer. And that was this dryer was going to process additional 2.6 million liters of milk. But there was no extra water available in that catchment. So our solution was, next click, please. When you look into the factory, this whole site was dependent on groundwater going after treatment, going to site reservoir and to the site. When we installed the new plant, the new powder dryer, we looked into the evaporator condensate or cow water. We treated in an RO plant, and then we were able to make the new dryer fully sustainable on the water it produced itself. To the level there was additional water available, with some further treatment, we were able to add that spare water or excess cow water back into the site reservoir and use it throughout the factory. So next click, please. So the way we did it, now we have 3 powder dryers. The overall milk capacity has increased almost to 3 times, from originally 1.4 million liters to now 4 million liters, but the water usage has dropped to 1 million liters. So if you look into water to milk ratio, earlier it was around 1.2, now it has dropped to around 0.25, 0.3. Was it straightforward? Is it just about putting capital in, recovering cow water? I think it was much more than that. I'll try to explain in the next slide. A holistic approach was required. First thing was around compliance, around the water quality. Being in New Zealand, we had to look into the Water Authority in New Zealand. We also needed to look into WHO regulations. But other important thing was around religious requirements, which is halal and kosher. I mean, a lot of our products go to rest of the world. So we have to look into specific requirements, especially around kosher needs for our products, which was quite tricky in this case, because depending on what the different ingredients were, it could have potential implications on the product being non-kosher. That means it won't be fit for purpose for that those set of customers. And then we also did a thorough scan of different customers and different markets for the products from that market. We just need to ensure that we have ticked all the boxes. And number 3 was very important. If you look into evaporator condensate, it's quite a pure water, lack of minerals. So there were concerns, what's the impact of that water now it is being consumed, not just for processing, but it is consumed as drinking water. And we had to bring in nutritional experts around it. So we had to have the careful balance between evaporator condensate and bore water to get the right ratio. And number 4 was staff and public perception, because now we are using evaporator condensate for drinking. We had to explain and go through proper change management to ensure that our staff and the wider community, because staff are also member of the wider community, that they understand the implications of what we are doing and what measures we have taken to ensure everything is 100% safe. Obviously, it had impact on the environmental footprint. And one of the challenges is around asset integrity, because evaporated condensate is quite soft water. There is a propensity to enhance the corrosion of stainless steel. Next slide, please. And this is another example from another factory on top of New Zealand. You may remember in the last example, we were treating evaporator condensate with a reverse osmosis process. In this factory, we didn't want to use a reverse osmosis. We had evaporator condensate available. As per the original design, that evaporator condensate wasn't used in the factory. It was being discharged into a natural wetland, and from wetland, it was going into a local river. If you see the name Wairau River, and on the top right-hand side, there is a condensate wetland. So what we decided to investigate was, what is the preliminary treatment capacity of the natural wetland, primarily around the volatile components which escape into the evaporator condensate. If we are quite happy with that preliminary treatment, can we bring that treated evaporator condensate as a feed source to the water treatment plant? and subject it to standard water treatment, and after that, use it as normal water, treated water throughout the factory. And I'm pleased to inform this project was very, very successful. In this case, the capacity is around 1.2 million liters. At times, we are using 700,000 liters per day, and the plan is to expand it to utilize the full capacity. And the last slide. This one was utilizing water which was reclaimed from milk when it wasn't pasteurized yet. So on the left-hand side, you can think of it's a milk protein concentrate process. We concentrate milk in UF membranes. So when we start with milk permeate, we put it through a reverse osmosis process. That becomes concentrated permeate on, and then the permeate coming out of reverse osmosis is a high quality water stream. And then we push it through the polisher and do the follow-up treatment. And there were some concerns. Could there be a risk of viral, let's call it microbial contamination, because the milk is not pasteurized? By putting proper controls in place and monitoring, like turbidity and conductivity at different stages, and also validating the treatment through microbiological testing later on, we were able to confirm that this process is quite safe, and the water we get at the back end is fit for purpose in direct product contact applications. So that's where I finish. And the last slide is more around my way of looking into the word. That when you talk of sustainability, it is not around environment. It is, we talk about holistic sustainability from a processor point of view. You look into environmental footprint, you look into larger acceptance in the community and from your customers, you look into technical viability, and you also look into financial viability. That's where you get the funding. So you carefully sow the seed, you nurture it, and eventually it will help with a prosperous and successful business. That's where I'll stop. Thank you.
Thank you, Dr. Bansal. I think very elaborate and very grounded presentation on water, its use, its reuse. You started with what is happening on this front in Codex, specifically Annex 4, where we are going to talk about the treatment technologies for reusing water, and you also talked about the development of IDF bulletin, which will provide a detailed guidance on use and reuse of water in dairy sector. You talked about role of water in dairy processing, stressing on optimal product mix, safety of products, and sustainability of operations. You emphasized a holistic approach, giving different aspects or dimensions of holistic approach as financial, technical, social, and environmental. You talked about sustainability aspects such as extent of sustainability and public acceptability, which is a very important aspect. Water procurement and treatment, its quality, quantity, integrity of assets in the dairy sector, in the dairy industry, and the wastewater. Everything that use comes back as a wastewater is a very forceful and strong statement in the context of water sustainability. You also talked about food safety, quality, health and safety, and environment and consumers in the context of sustainability. While talking about impact of chemical treatments, you emphasized that disinfection cannot be compromised in view of generation of its byproducts. Nevertheless, you need to monitor whether we are not overusing or overdosing disinfectant. You talked about the strategies on water use and reuse, emphasizing upon reduction, reusing, without processing, with processing, and controlling waste. And where necessary, to also invest in water reuse technologies. You also focused on end-use applications involving treatment and storage, and if this treatment and storage were required, what are the possible actions that one needs to take. You give an example of reuse of water from evaporator condensate, and how in your organization you were able to triplicate the capacity or triple the capacity of processing without any additional use of water, and that is commendable. He also talked about importance of holistic approach, focusing on different aspects and very important ones, including compliance, consumer or market acceptability, the health part, the staff and public perception part, because without their involvement, it is not possible to go ahead, the environment footprint, and also the integrity. We also talked about the safety of water that is drawn from a product like unpasteurized milk. So overall, a very grounded presentation, a very well stressed approach on holistically approaching the concept of use and reuse of water. So thank you, Dr. Bansal, for your very enlightening presentation. And if I may ask a few questions, you have talked about water to milk ratio. So is there any best practice, any best number in this context which you would like to share with the viewers?
In terms of best practice water use, look, there is a misconception that there should be one fixed number, but the amount of water required by a dairy factory will depend on what products it is made. Like when the milk comes into factory, of course, for milk reception, milk treatment, tanker wash, the amount of water required will be same whether you make milk powders or you make proteins. So let's think of, let's say we bring in 100 liters of milk. For milk powder, probably you need 50 or 60 liters in total. But if you start off making cheese is the first thing. Then after cheese, you have whey. After whey, then you need to look into lactose and minerals. It could very well be for 100 liters of milk, for all those processes, it could be 200 or 300 liters of water required, and still it will be working best practice. But although you are using around 5 times more water for the same bucket of milk. So the concept is, depending on your product mix, and if I add the complexity, what is the size of your processing plant? And how well have you maintained it? What is the design features of it? All those will have a significant impact on best practice. As I said, for a small factory, our water to milk ratio was 0.25 or up to 0.3. Whereas for some factories, we have 2.2, 2.3. Yep, that's it, Aditya.
Yeah, thank you. There seems to be some problem with the communication. So another question for you, Dr. Bansal, is what could be the key parameters that will affect reuse of reclaimed water? So briefly, if you would like to say, you have already covered in detail some of these aspects, but what are the key parameters that one needs to focus on?
First and foremost, if you look into what is the business driver, is it a target for your company to reduce water footprint because this is due to limited availability of water in that area where your factory is? Are you looking for future expansion, or your environmental constraints are driving you? Or public is, the perception of the public is you are using too much water. And once we have covered that, what is the reuse water? What are the sources of that water? When you look into evaporator condensate, generally it is very clean water. But when you look into membrane concentrations, if you concentrate milk or whey, water is very high quality, except urea goes through. urea is present in milk, especially in grass-fed processing areas. Urea passes through into reverse osmosis permeate. That poses restrictions on the level of chlorination you can do because there is chances of disinfection byproducts. And then the other driver it is, if you want to store that water, say you bring it today, but you don't have the ability to use it for another 12 or 24 hours, there is propensity for the biofilm to grow. So in that, how do you keep it clean? I wouldn't use the term sterile, but how do you keep it clean enough and you can control the microbial growth so that water is still fit for purpose? So depending on, so you need to look through a number of factors to ensure that the water you have, you are spending the least amount of money and you are getting the safest water. Yeah, that's it. Aditya, thank you.
So thank you, Dr. Bansal. I think you have very lucidly explained the importance of use and reuse of water and the technologies involved and the different aspects involved for it to be holistic. So I think we are already past the time that we had allocated for this webinar, but there are a few interesting questions, and so I would like to take at least a few of them. So one question is for Dr. Everett. We would like to understand what effect do the different heat treatments of milk have on cheese quality?
Yes, with different heat treatments, you will get inactivation of different enzymes, which may be important for flavor and texture development in cheese. So that needs to be considered, which is sometimes you may want to use a lower heat treatment, such as thermization of milk, to allow the enzymes to act to produce a more flavorful cheese. In my opinion, I would think that you do get differently flavored cheeses if you use raw milk. Whether it's better than pasteurized milk cheese is open to discussion. So I think it's the taste is in the mouth of the beholder, so to speak. But I think that it is important to get the right flavor development that you want. If you omit heat treatment of milk, there are still many preservative functions that are available in cheese making to make sure it's a safe product. So things like the production of acid, the culturing, the dehydration to remove most of the water, salting, cooling, packaging, all those things tend to act in a cohesive way to protect the safety of the cheese. So if cheese is made carefully and correctly, you can omit the pasteurization step.
Thank you, Dr. Everett. Another question, I think we have quite a few questions, but I'll take one question each for each speaker because we are already past the time. So Dr. Bourdichon, there's a question for you. Monitoring of listeria, probably you talked that this should be done about genus level. Will it not be very stringent for food manufacturer? So that is a question one of our viewers has put up for you.
So the focus today was on cheese environment. When it comes to cheese environment, you do not expect to have Listeria spp in your environment. So this will not change so much in terms of workflow for the cheese manufacturer. What it will be very helpful is to be more proactive, because we know that in terms of ecology, Seligerie, Velchimeri, Inocua, and other species are first comers rather than Listeria. So it's in a way to be more efficient in processing environment monitoring and to stay at a low alert level zone rather than to go in a high alert level zone. This approach is not possible in every food matrices types. In the fish industry, for example, when there is naturally a prevalence from the raw fish, particularly in salmon, on Listeria spp, it's not approach. But for the cheese, no, it's not that stringent. What is very stringent is when you discover Listeria monocytogenes, and it's too late. Then you need to go in panic mode, you need to upgrade the monitoring on the finished product, you need to inform the authorities, you might have to stop the facilities. which all these points could have been avoided if you have reacted from the start with Listeria spp. So it's a little bit more work, but it's more relevant in terms of what do you expect from the processing monitoring, which is not having a finished product contamination at the end of the day. So it's not so much work, but it's a little pain, but the gain is pretty huge.
Thank you, Dr. Bourdichon. I think the point is well taken, that it is the context which decides the efforts that you put in for monitoring. So for cheese monitoring, it is important that you monitor Listeria at genus level. You don't want it to be present there. Another question is for Dr. Binsel now. And I think I would make this as a last question. Dr. Bansal, the question from one of our viewers is, are you using any technologies such as cold plasma or its variants for cleaning of or cleaning the water, or for any kind of water treatment for its reuse?
The simple answer is not this particular technology. On our radar, we have been exploring a number of technologies. Of course, reverse osmosis is our technology of choice. We are looking into advanced oxidation also. We have looked into natural technologies like wetland, and we are also trialing some other technologies. But cold plasma technology hasn't been on our short list of technologies, but we have watched and brief on multiple technologies from around the globe. Thank you.
Thank you, Dr. Bansal. So now to close this webinar, I think going with the efforts of IDF to disseminate latest information in the field of dairy sector, I think this webinar has covered very nicely the evolution of heat treatments of milk, the science behind it, the processing the monitoring of processing environment, in particular for cheese and also for other products, the importance of presence of pathogens and the ways to control them, and also on the important aspects which is becoming more and more important, uh, that is on use and reuse of water. So with this, I would like to thank IDF for organizing this webinar. I would also like to thank our distinguished speakers and the audience. Thank you.